Hi everyone, my name is Jackie Beck. I'm a PhD student at MIT, and I'm very excited to share with you our paper, The Limits to Learning a Diffusion Model, which is joint work with Vivek Farias, Andreea Georgescu, Retsef Levi, Tianyi Peng, Deeksha Sinha, Josh Wilde, and Andy Zheng. So let me first give an overview of our paper. So as the title suggests, we study the limits of learning to two fundamental diffusion models. So the first model is the SIR model, which is a fundamental building block of epidemic modeling. So a lot of models that you have probably seen in the past year forecasting the pandemic are often built off of the SIR model. It is an extension of the SIR model. So we are going to study the most basic model in this literature. The next model we study is the BAS model, which has nothing to do with modeling pandemics, but it's used to model consumer adoption for new products. So, for example, if you want to model how many people will buy the new iPhone, you can use the BAS model to model this. And this is also a fundamental model in the marketing literature. So both of these models are similar, very similar mathematically, which is why we study them together. And for both of these models, one of the key use cases is to do forecasting. So, you would want to forecast how many people will be infected for the SIR model, or for the BAS model, you want to predict how many people will buy your product. So to do forecasting, you essentially need to estimate the unknown parameters of the model. And I'll explain the parameters of the model in the next slide. So the question that we ask is, how much data is needed to accurately learn these models? So this is a very fundamental question that we ask, and I'm going to give you the punchline of the paper. And so our main result says that you actually cannot hope to learn the model early on in the process. And I'm going to make formal what's early on sort of later on in the presentation, but this is a very negative result because early on is essentially when you want to do forecasting in the first place. Like if the pandemic has already passed, then you don't need to do forecasting. You want to do the forecasting early on. So this is a very negative result, saying that we use a information theoretic lower bound to show this impossibility result. So, but our theoretical result does not say it's completely hopeless to do forecasting because our result does use some assumptions that one can try to go around. So we present one workaround for this fundamental limits to learning that we implemented for COVID-19 forecasting. So for the rest of the talk, I'm going to first describe the two models, and then I will describe the main result, and then I will describe the workaround that we implemented. Okay, so first let's describe the SIR model, which is defined by these three differential equations. So what this model does is that it separates the population into three compartments, S, I, and R, and the differential equations dictate how quickly people move from one compartment to another. So for people getting infected, essentially people who are already infected infect people who are still susceptible at rate beta. So beta is a parameter that determines how quickly the infection spreads, and then people recover at rate gamma. So there's three parameters to this model, beta, gamma, and n, which is the population of the system. And if you knew what these parameters were, then clearly you can just kind of plug it into the differential equations, draw out the curves, and answer any questions you might have about the future. So we need to essentially learn these three parameters. And I want to mention that we treat the parameter n as unknown, which you might think is initially kind of weird because, we do know the population of particular countries or states. But for example, in COVID-19, N was unknown because of both asymptomatic cases and limited testing. So this is because in our data, we don't actually observe everyone who got infected with COVID. We only observe a certain fraction of everyone who got infected with COVID, and this fraction is unknown. And this is equivalent to assuming that N is unknown. So you can think of N as some fraction of the total population, and this fraction is unknown. Okay, so now moving on to the BAS model. So the BAS model is very similar, but it only has two compartments. So adopted refers to the population that have bought this particular product that we're interested in. And the mechanism for people buying the product is very similar in that people who already have bought the product kind of influence other people to buy the product. So this is essentially this term is the same as in the SIR model, but there's also an additional term which represents innovators who adopt the product without any influence. So there's this additional term here. So here there are also three parameters, beta, p, and n. And n here actually represents the eventual total number of adopters. So in the BAS model, actually, when t goes to infinity, everyone who is susceptible ends up adopting the product. So n represents the total number of people who will buy the product. And clearly, this quantity is unknown a priori. In fact, this is one of the main parameters of interest when you're doing forecasting. So in both settings, so these are the parameters, and n, the population, is an unknown parameter. Okay, so for the remainder of the talk, I'm actually going to focus on the SIR model, but all of our results do hold for the BAS model. And the SIR model is a bit more complicated to analyze because of the fact that there's a recovered compartment. So we'll state our results with respect to the SIR model. Okay, so let me just write the model again, and I'm actually going to refer to this SIR model as the deterministic SIR model for reasons that will become clear in 1 second. So the question that we ask is, okay, so when is it possible to, accurately recover these three parameters? And our first result is actually positive. It says that if we observe the infection curve, IT, for some very small amount of time, then we can actually identify all three parameters. So this result is essentially saying that if the parameters change by a bit, then the infection curve will also change by a bit, right? So the infection curve essentially uniquely can identify the parameters. So this result says in this deterministic model, we can identify the parameters. But of course, in the real world, the reason why we might not be able to identify the parameters is because of noise. And this model does not take noise into consideration, which is why we need to consider a new model, which we call the stochastic SIR model. So we consider what's called the continuous time Markov chain variant of the SIR model. So let me explain exactly how this model works. So we index the process by events, where an event is a new infection or a new recovery. So anytime one person moves from the S to I compartment or the I to R compartment, this is called an event. So then we're going to let the state of the system be SMIMRM, which is the state of the system after the nth event. So for convenience, we just let CM be the total number of people infected by after the nth event. And so now we have to specify sort of how often these events occur, which we will call TM, which is the interarrival time between events. And this is going to be random. So it's going to be distributed exponentially. But actually the mean of this process is going to be exactly the same as the deterministic model. So essentially what this says is that this term refers to the infection. So this term is essentially the same as this term. And the second term is essentially the same as this term, how quickly recoveries occur. So an expectation at each time step, we have we follow kind of the deterministic model expectation, but but the interarrival times are exponentially distributed. So and then at each event we have to specify whether the event was a infection or a recovery. So it's an infection with probability this term divided by the entire the sum. And the observation set, what we observe by time m is OM. So here we observe both the interarrival times and whether it was an infection or not. So this is the observation set. And so the question we ask is, given these observations, can we estimate these parameters? Okay, now I'll state our main result informally, which says that it is statistically impossible to accurately recover the parameter n until the process is 2/3 of the way to the peak of new infections. So what exactly is the peak? We define it as the time when the rate of new infections is the highest. So essentially when the derivative of the infection curve is the highest. And it is easy to show that this point occurs when a constant fraction of your population has been infected. So this is pretty late in the process because a constant fraction of everyone has already been infected. And what this is saying is that unless you're 2/3 of the way there, of the way to the peak, you will not be able to recover the parameter n. So this result only has to do with the parameter n, and we'll show in the next slide that actually the other parameters are easy to estimate. But the parameter n is very important because if you get n off by a factor of 2, then your estimate for the total number of people infected will also be off by a factor of 2. Okay, so the way we prove this result is in 2 steps. The first step is essentially our main result. This is the Kramer Rao Bound. And what this says is that if given your observation set OM, if you let n hat be any unbiased estimator of n based on these observations, then the variance of your estimator will be at least as large as n to the 4 over m to the 3. So what exactly does this formula imply? Well, if you want your estimator to be accurate, you better hope that the variance of your estimator is at least as small as n squared. Because if your variance is n squared, then the standard deviation will be n. And ideally, you want the standard deviation of your estimator to be smaller than the value itself that you're trying to estimate. So if you essentially plug this n squared in here and just rearrange, what you get is that you need m to the 2/3 number of events before you'll be able to estimate n accurately. So this result is in terms of the number of events, and the next result will convert the number of events m to real time, which is how the main result is stated. Before I move on to the next result, let me say a couple words about the proof of this theorem. So essentially what we need to do is, for the Kramer Rao bound, we essentially need to compute the Fisher information of n based on the observations OM. So essentially this is how much information is OM conveying about the true parameter n. And the reason why this is non-trivial is due to the fact that OM is this long sequence of random variables that has this non-trivial correlation structure. So to tackle this, what we do is we take advantage of the conditional independence between many of these variables, which allows us to break down the Fisher information into sort of smaller Fisher information terms that are sort of more manageable to analyze. And the second hurdle in proving this result is actually the fact that the SIR model can terminate at any time. So if everyone who's currently infected recovers without infecting anyone else, then the pandemic would just end. And there, at any point in time, there is some probability that this happens, although this is low. But we do have to, take this into consideration when we're doing the analysis. And we actually don't have to do this in the BAS model, because in the BAS model, everyone sort of becomes infected eventually. It's just a matter of sort of how long it takes. So this is why the SIR model is sort of more complicated to analyze than the BAS model. Okay, so the second result just says that the amount of time it takes to get m to the 2/3 events is just 2/3 of the way until the peak. And sort of the intuition for this result is the fact that sort of initially at the beginning of the pandemic, the infection curve sort of resembles an exponential function. So we use this intuition to prove this result. Okay, so our main result shows that the parameter n is hard to estimate for both the SIR and BAS models. And our next result actually shows that all of the other parameters are much easier to estimate. And we prove this by constructing explicit estimators for these parameters and show that the variance is small even with a small number of samples. So now I want to talk about sort of how to get around Theorem 1, the limits to learning for parameter n. And I want to highlight two assumptions in the theorem, the unbiased estimator and the based on OM. So in reality, we actually have a lot more data than just these observations. We have data on how COVID-19 transmitted in other countries, or we have data on things like when the lockdowns happened or mask mandates. So we can often use these other information to construct, priors for n, which will bias the estimators in an informative way. So let me describe to you the implementation that we took for COVID-19 forecasting. And our goal was to do county-level forecasting for COVID-19 infections. And the main thing that we took advantage of is the fact that there's wide heterogeneity among the counties. So here I'm showing you the daily new cases for 6 different counties, all in Georgia, where you see that the counties on the left have a very different looking infection curve than the counties on the right, even though they're for the same time frame. This was March and April last year. So essentially the counties on the left have already peaked. Their infection curves have already peaked, while the counties on the right, they have not peaked. So in terms of the theory says that for these counties, we can actually estimate all the parameters, whereas for the counties that have not peaked, we won't be able to estimate them. So what we're going to do is we're going to use the parameters learned from the peaked counties to help us learn for the counties that have not peaked. And so we use this sort of two-stage approach, which I won't go into the details of, but essentially we show that this two-stage approach sort of works in that, so this is the y-axis is error, and our approach is the blue line. And the main thing we want to compare to is the red line, which is the approach where we just estimate all parameters at once, just without sort of kind of separating out the peaked and non-peaked counties. So this is kind of the most naive approach. And we show that our approach does a lot better. And the purple line is just the line where if we knew the n in advance, how well we can do. And clearly this is very small. So to summarize, we essentially show that we early on forecasts can be very inaccurate, and we have to be very careful in both making predictions and using these forecasts. And I think the most valuable direction for future work is coming up with new heuristics or workarounds like the one that we showed to sort of get around this limits to learning. Thank you so much.